Welcome. In this video, I'm going to start going through the paper 2 questions from the new exam started in 2016. So it's still 50 questions, and if we move on to the second slide here, it starts with an experiment. They're talking about 2 IB students carried out a project. They're telling you about this titration they do. Appears to be some redox going on. And if you scroll down to the first question, it says calculate the volume in centimeters cubed of 0.01 molar Na2S2O3 required to react with iodine to reach the end point. And so if you look, you're given 3 titrations. And if you do the math here to find out the volume for each titration, you'll see that this first one is 23.95 milliliters. But when I subtract the other 2, this one is 22.05, and the last one is 22.15. And so what you're supposed to realize is this was a rough titration, so this is not going to be part of your average. You're only going to average the second and third titration and assume the first one was just a rough titration to get a better idea, refine the idea of how much they actually need. So my average is going to be 22.05 plus 22.15 divided by 2, which means my value is 22.10, and the proper label would be milliliters. And they're not asking you to show the uncertainty, so don't feel like you need to, because this is simply a 1-mark question. Then, continuing with the same question on the next page, calculate the amount in moles of sodium thiosulfate that reacts with the iodine. Well, remember we had 0.1 molar, 0.100 molar strength used, and we know that we're using a total of 0.02210 liters if we convert our milliliters to liters. So remembering that this is moles per liter, if I multiply this by the liters used, and again, I have to convert my 22.1 milliliters to liters. Now when I multiply, I see that I've got 0.002210, and you certainly could express this in scientific notation if you find that easier. But that is my moles of sodium thiosulfate that I've used. Now they ask you to calculate the concentration in moles per liter in the diluted bleach solution. So first of all, we have to find out, compared to the sodium thiosulfate, which we've got a molar amount for, how many moles of ClO or hypochlorite ions would that be? So the 0.002210, this is the Na2S2O3, and I can see that there's 2 moles of iodine ions per 2 moles of the thiosulfate ions. And then I see that with the other equation, there's only 1 mole of hypochlorite ions per 2 moles of iodine. So I need to do both calculations to convert my moles of thiosulfate to moles of hypochlorite ions, and that gives me 0.00105 moles of my ClO minus ions. And my diluted bleach solution, if you read, was 250 milliliters or 0.250 liters. So that means my concentration is 0.0042 molar. And you notice I've dropped to 2 sig figs because the 250 milliliters didn't indicate that all 3 were significant figures. Moving on to part 4, calculate the concentration in moles per liter of hypochlorite ions in the undiluted bleach solution. So this one's a little easier because I already know that I have 0.00, make sure you can see my decimal, 0.0420 molar. Part B, so again, still working with the same information. they want you to deduce the oxidation states of chlorine and iodine in the following species. Well, chlorine is going to be likely a -1, but we need to double check. Sodium's a +1. Oxygen's it's -2. So chlorine in this instance is actually forced to lose some control of its electron, and it picks up a +1 oxidation state. I2, however, is going to be at 0 because there'll be truly a covalent bond occurring there. Question number 2, deduce with the reason the oxidizing agent in the reaction. So if I look at the reaction, I start with ClO minus plus 2I minus plus 2H plus, and it yields Cl minus plus I2 plus H2O, and I should be in the box, but I'm not. And when I look at that, if I assign oxidation states, I know chlorine is going to be a +1 here because the oxygen gets to remain -2. This is a -1, is indicated by the charge. Make sure you can see that there. This is a +1, is indicated by the charge. -1 is indicated. 0, +1, and -2. So if I look for change, I see chlorine went from +1 to a -1, and that indicates it's been reduced. And that therefore makes it the oxidizing agent. Part 3 says, from a health and safety perspective, suggest why it's not a good idea to use hydrochloric acid when acidifying the bleach. Well, if we think about chlorine being in the place here, this is HCl, would provide a chlorine ion here instead, then over here we could expect to produce Cl2, and chlorine gas is toxic. So we could expect chlorine gas would be a product and is toxic. We don't want to be producing that, especially when there's an easy alternative. Part 4, the thiosulfate ion, S2O3 2, is an interesting example of oxidation states. Sulfur atoms can be considered to have an oxidation state of +6 on one atom and -2 on the other atom. Discuss this statement in terms of your understanding of oxidation state. So the +6, I'm going to assume, arises from this middle sulfur, and it's because this sulfur, I could say one sulfur, do it a little better than that so you can tell what I'm talking about. Carbon gains oxygen and is oxidized. That's an old definition. Another thing we could say is carbon loses hydrogen to be oxidized. Or another valid statement would be carbon goes from oxidation state -4 to +4, showing it's oxidized, or showing oxidation. Those would all be valid statements about what's going on. An invalid statement would be to say that loss of control of electrons forms ions. Sometimes that's true, but in this case, it hasn't formed an ion. So there's a couple examples of valid and invalid statements you could be making. Then state the condensed electron configuration of sulfur. If I go with the noble gas configuration, it'd be Ne, 3s2, 3p4. Or another way of condensing it, and I'm not quite sure which one IB is opting for here, would be 2, 8, 6. Part 2, deduce the orbital diagram showing all orbitals present. Well, working off my 286 there, I have a 1s with 2 electrons in it. I have a 2s that is full as well. I have a full 2p. I have a full 3s. And my 3p has got 2 unpaired and 1 paired orbital. So that would be my complete orbital diagram. Number 2, one of the main constituents of acid deposition is sulfuric acid, H2SO4. This acid is formed from the sulfur dioxide pollutant SO2. Then they show the mechanism here, and they want to know, what does the symbol, this little dot, represent in the species shown in this mechanism? And that is what we call a free radical. Or if you want to, you could describe it as an unpaired electron. Part 2, draw one valid electron dot structure for each molecule shown. So for SO2, I know that I have 3 atoms with 6 electrons each, so I have 18 electrons to balance this thing. So if I attempt to bond the SOs, the 2 oxygen, with just single bonds, I can see I would still need 2, 4, 6, 8, 10, 12 more electrons in each oxygen, plus 14, 16 on the sulfur, for a total of 20 electrons. And I don't have 20 electrons, so I'm going to be forced to put a double bond on one of these oxygen. So this molecule would have some resonance. That would leave me a pair of electrons, a lone pair for the sulfur, 2 lone pair for this oxygen, and 3 lone pair for this oxygen. And when I count up, that uses a total of 18 electrons and satisfies all 3 atoms. H2O is much simpler. I have a total of 8 electrons to use here. So the oxygen bonded to each hydrogen. Hydrogen can't form a double bond, so this is going to have to work, and it does. I end up with 2 lone pair on the oxygen, and each hydrogen single bonded for a total of 8 electrons. Part 3, deduce the name of the electron domain geometry and the molecular geometry for each molecule. So if remember, we have sulfur with a double bond here, a single bond here, and a lone pair. So the electron domain is trigonal planar. So they would like to be at 120-degree angles, but that lone pair crowds the 2 oxygen and creates a bent shape, or if you prefer, call it a V-shaped. H2O would like to be linear if it could. I guess the SO2 would too without the lone pair there. But with 2 lone pair, its electron domain is actually tetrahedral. But the 2 pairs force this is to be bent, or sometimes it's called double bent because of the 2 lone pair. Bent or double bent. Or again, V would be just fine. And then part 4, deduce the bond angles. Well, trigonal planar would be 120 degrees, but because the lone pair is crowding it, it's going to be less than 120. But it should be more than 115. So something in that 120 to 115 degree range would be acceptable, to know that it would be trigonal planar if it were 3 atoms and not a lone pair there. H2O, tetrahedral, would be 109.5, so it's going to be less than the 109.5. Probably around 107 with 1 lone pair. So with 2 lone pair, maybe around 105, 104.5. That would be the range I would be looking for on this one.